Welcome to EDU World Space.
So here we have a diagram of the initial conditions of the system. We have A moving with momentum ma va prime, so its initial velocity is va prime, and B moving with momentum mb vb prime. The system is rotating with angular velocity omega. The center of mass G is moving in that direction with momentum m v bar naught. So let's look at the initial conditions of the system. So this is before the cord breaks. So initially, let's first find the location of G, the mass center. So we know that the definition of mass center tells us that the distance between A and G, AG, over the mass B is the same as BG over the mass of A. And this is equal to AG plus BG over mass A plus the mass of B. And so this is the total length between A and B, which is L, we'll call it L, over the total mass of A and B, M. So this implies that AG is equal to MB over the total mass M times L. And this is equal to 1 over 3 times L. And similarly, the distance BG is equal to MA over M times L, where L is the length of the cord, which we wish to find. So that's 2 over 3 times L. So firstly, we'll find the linear momentum of this initial state. The linear momentum, we'll call it L naught, is equal to the mass of the system, the mass of A and B combined, times the velocity of the mass center, v bar naught. And so this is 3 kgs times v bar naught. The angular momentum about the mass center, about point G, is as follows. So this is the initial angular momentum, hg naught, and this is equal to vector GA, the line between A and G, cross with the momentum of particle A initially, ma va prime, plus gb for particle B, cross with particle B's momentum, mb vb prime. That's linear momentum. So this gives us this expression, which is the position crossed with the linear momentum gives us the angular momentum about point G. So substituting our values in here, this is 1/3 L times 2 kgs times 1 over 3 L omega, since V is R times omega, which is 1 over 3 L times omega for ball A, and that's in the K direction. So we'll do the same for ball B. It's 2 over 3 L times the mass 1 kg multiplied by V, which is 2 over 3 L omega K, where omega is the angular speed with which ball A and ball B are rotating about G. And so simplifying, we get the angular momentum about g to be 2/3 L squared omega times basis vector k. So that's our angular momentum for this state about the mass center G. So next we need to calculate the kinetic energy. So if we use all these conservation laws, we can then equate the two after the quad breaks. Hence we calculate the angular momentum, kinetic energy, etc. So the kinetic energy T naught is equal to a half m v bar naught squared, where v bar naught squared is the speed of the mass center, or v bar naught is the speed of the mass center, plus a half of the sum of the individual contributions to the kinetic energy. And so this is a half times 3, which is m, times v bar naught squared, plus a half ma va prime squared, which is a half, into the mass of a 2 times its velocity 1/3 L omega squared. That's the same for ball B, which is a half, into 1 into 2/3 L omega squared. And so we get an expression for T naught in terms of L and omega to be 3/2 V bar naught squared plus 1/3 L squared omega squared. This is actually a 1/3. So this is our kinetic energy before the quad breaks. After the quad breaks, we have the following situation. Ball A moves away vertically with respect to our axis, so parallel to the y-axis, at a separation of 2.56 meters from the y-axis. Ball B moves diagonally towards the x-axis with momentum mb/vb. Ball A's momentum is ma/va, and the separation between the y-axis and the point at which ball B intersects the x-axis is 7.48 meters. So this is our situation, our final situation. So now, since we calculated our linear momentum initially, we can apply the conservation of linear momentum after the quad breaks. So the conservation of linear momentum tells us that the initial linear momentum, mv bar naught, was equal to ma va plus ma plus mb vb. So the linear momentum of the two balls as they move apart. So remember, this is 3 v bar naught, and this is equal to the mass of A times its velocity, which is 5 in the j direction, plus the mass of B times its velocity, which is 7.2 I minus 4.6 j. And so this simplifies to 7.2 I plus 5.4 j. And this is perfect because from here we have one equation with one unknown. And that unknown is what we initially wish to solve for, which is the initial velocity of the center of mass G of the two balls when they are connected by the cord. And this vector, we divide both sides by 3 in that equation, and we get v naught bar to be 2.4 meters per second times basis vector I plus 1.8 meters per second in the y direction, j times 1.8. So we have calculated our initial velocity of the mass center of our two balls, 2.4 meters per second I plus 1.8 meters per second j. Now we still need to calculate our velocities or our angular speeds and the separation between the two balls. So we'll apply the conservation of angular momentum about O. Since we calculated the angular momentum initially, so the angular momentum conserved about O is 1.89 j cross with m v bar naught plus h g naught. Remember, we have an expression, we have an equation that relates the angular momentum about h g, about the point G, the mass center, to the angular momentum about the origin. And this is equal to 2.56 I cross with MA VA. This is the angular momentum about point O after the quad breaks, plus 7.48 I cross with MB VB. So substituting for V bar naught, HG about H about G, the angular momentum about G originally, HG naught, for VB, VA, and for the masses, we get the following. We get that 1.89 J cross with 3 into 2.4 I plus 1.8 J, which is V bar naught, plus 2/3 L squared omega K is equal to the right-hand side, which is 2.56 I cross with 2 times 5J plus 7.48 I cross with 1 kg, the mass of B, times its velocity, 7.2 I minus 4.6 J. So simplifying this equation, we get minus 13.608 K plus 2/3 L squared omega K is equal to 25.6 K minus 34.408 K. So all of these are K components, and so we can just equate them as is. And so what we end up with is that L squared omega is equal to 7.2. So if we simplify the equation, we get L squared omega is equal to 7.2. We'll call that equation 1. So both of these are unknowns, and both of these are what we wish to solve for. So if we call that equation 1, we can then turn to the conservation of energy. Remember, we calculated the kinetic energy before. So using the conservation of energy, we can set up another system of equations. Conservation of energy tells us that T naught, the initial kinetic energy, is equal to the final kinetic energy. T naught is equal to T. And applying this, we get 3 over 2 V bar naught squared plus 1/3 L squared omega squared, the initial kinetic energy, is equal to the final kinetic energy, a half ma Va squared plus the contribution by ball B as it moves off, a half mb Vb squared. So again, we can substitute values into this equation. So we get 3 over 2 into 2.4 squared plus 1.8 squared for each component of the initial velocity of the mass center, plus 1/3 L squared omega squared is equal to a half into the mass of A, 2 times 5 squared plus a half times 1 into 7.2 squared plus 4.6 squared. So we can see from here that we actually end up with a long equation. However, there's only 2 unknowns. So one equation again with 2 unknowns. And if you rearrange, we can write this as L squared omega squared is equal to 144. And we can call this equation 2. So now we have 2 equations with the same 2 unknowns, L and omega. So if we take equation 2 and we divide it by equation 1, we get omega is equal to 144 over 7.2, and we actually solve for omega, which is 20 radians per second. And that is our answer for part C. And then we can simply take this value for omega and substitute it in equation 1. So if we substitute this value for omega into equation 1, we get that L squared times 20 is equal to 7.2. And hence we get the length of the chord L to be 0.6 meters. 0.6 meters is equivalent to 600 millimeters. And that's our answer for part B.